Hello, a great welcome to the series on PLAXIS. This is a part 2 of Tutorial 3, which will discuss mainly the verification of a Raft foundation subjected to a set of loads. So I would request the audience to go through part 1 of this tutorial before switching over to this part. So this part will essentially start with the staged construction, will perform the calculations and then perform a review of the results obtained from PLAXIS in the post-processing mode. So let us start with the PLAXIS again. Fine, so let us proceed to the staged construction, wherein we will be able to define the various stages. By default, the PLAXIS start with the initial phase. So just double click it. You'll find that the calculation type is chosen as scheduled procedure, and adopts this procedure in order to have a calculation of the vertical stresses, effective vertical stresses, as well as the lateral stresses. Now other parameters are okay for me. This is okay. Now in this case, we need to ensure that yes, all the soil volumes are selected. Okay, so this is my model. So if I saw the soils, soil 1, soil 2, everything is okay. And let me just go to my geometry and the soil volumes. Both the soil volumes should be active. Yes. So the soil volumes are active, as you can say. So this is all regarding the initial phase, which simply calculates the stresses in the soil before the construction of the structure. Now please ensure that in this initial phase all the soil volumes are active, the plates are not activated, point loads are also not activated. Okay, so now let us straight away go for the next phase. So just double click it. I want that this phase represents the basically the excavation as well as the foundation, excavation and the foundation. Okay, and we are using a calculation type of plastic, and I will set all the parameters as default here. There is no change as such, so I will keep it as okay. And here obviously we need to ensure that the volume 2 that represents the excavation, so here we can say that this volume need to be set to off. So that is done. And during this phase, please also ensure that the plates are activated. Yes, the plates are activated. So if you want to see the model, you can say that this would be how the model looks like. We find that the soil portion is excavated, and all the basement walls and the basement floors are active. Okay, now after this, so if you just click it, you will find that the procedure used is the plastic one. Okay, that's okay for us. Now let us proceed for the definition of the important stage. That is, we need to provide the column loads in the next phase. So add one more phase, and this phase, just double click it. I want to rename it. So I will call it as a, for example, it is a phase wherein I want to apply my dead load, lie load plus wind load column loads. Okay. So this is for easy verification, easy indication. So that is done. And now in this phase, I want to ensure that all the displacements that is created, unwanted displacement created during the excavations are deactivated. That means I will use in this particular phase reset displacements to 0. This is very important for us. So that is okay. Now in this phase, that is phase 2, we have got an initial phase 1, and then finally the phase 2. Phase 2 is very important to us, and in this case ensure that we activate all the point loads. But if you remember, we have applied the column loads as unit loads. Now in this phase we need to replace these unit loads with the actual vertical column loads. So you'll find that all the columns are having the different loads, and because of this is not a case of a symmetry. That is why we have modeled the entire raft for this case. So let us activate the point loads over here, right? So let us start filling the actual point loads. For example, if you see the point load 1, let us see what exactly the point load is. Let me just zoom this once again, because we are interested only in this area. Just rotate this a little bit towards this side. Okay, this should be good enough. Now it is important that we apply all the loads, okay, very clearly, okay, at the right location. So first we need to identify which these column point loads are. So you can just make it off. So you'll find that yes, this is the extreme column load. So just press it on, and now we know we need to apply the right load over here, and we know that the corner load is basically there is a 2500 load, right? It's a minus, that is a F set. That's a minus 2000. It is not unit. It is minus 2500 kilonewton load. So that is okay. So you'll find that yes, here you can see that this, and so the arrow has increased. So minus 2500 kilonewton is applied. Now let us proceed to point number 2. First see which point is this. Just so yes, this is this column load. So what we can do is that you can just press it, okay, and this column load F set, it is basically it is a minus 4500. So just apply this minus of 4500. Okay, fantastic. So we applied the two column loads. Now let us go to the third point. Obviously the third point is this column. So what we can do is can activate it, just apply F set. In this case it is a minus of 4500 F set component. So in a similar way, let us also apply the final load over here. Sorry. So we can say that that obviously represents the point 4. Go to the point 4. You can see that yes, this is deactivated. It's the right location. So here we know that the load will be minus of 2500. So apply my F set as minus of 2500 Newton. Okay, fine. In a similar way, what we do is that we start applying or modifying the other loads. So 0.5, it must be this load. Let us just see whether it is the same point. No, this is 0.5 is here. Okay, so we need to apply the right load at the right location. So let us apply it. So we know that this load is minus of is a corner load. So it should be lesser one. It should be minus 3000. Minus 3000. That's good enough for us. Minus 3000. And now let us go to point number 6. Point number 6. It should be my 6. It must be my 5000 load. Okay, so I will apply it as a 5000. So this should be minus 5000 kilonewton. Okay, good. So this means that we have point number 6 completed. Go to point number 7, and point number 7 is this column. Okay, fine. That should also be same as the earlier load, that is equal to 5000. So I will have my 5000 minus 5000 load deficit. Fine. So we have only one point remaining, that is point number 8. And the point number 8, obviously we have a lesser load, that is minus 3000 kilonewton. This means that in the phase 2 we have replaced all the unit loads with the actual loads, and as you can see that the four corner columns are having one range of loads, and the intermediate columns are having a larger loads as shown by this arrow. That's also a quick check for us. Okay, so all the loads are being fed into this. Now we are ready to move to the calculation step. So remember, we have basically the 3 calculation stages. That's the initial phase, followed by an excavation phase, phase 1, and the final, the load plus live load plus wind load, phase 2. And in this phase 2, we would like to calculate the actual direct stresses as well as the displacements of the settlement below the foundation. Okay, so now let us proceed for the calculate button. So calculate. So okay, no stress points are selected. That's okay for us. So proceed for the calculation. So as you can see that yes, the calculating phases are in progress. You can just press the details. You'll find that yes, calculations are in progress. Once the calculations are in progress, we can go to the post processor and inspect all the results. Here we'll be examining as far as the soil is concerned, the deformations under phase 2, the stresses under phase 2. Also, we would like to see, for example, the bending moments as well as the settlements relevant to the basement floor as well. Okay, fine. So let us proceed for inspecting the results because the calculations are completed. So as usual, obviously, to verify the accuracy of the results, we have to start with the initial phase. So in the initial phase, we would like to see the distribution of the total stresses as well as the effective stresses across the depth. So let us just press the stress button, and here we shall first proceed for the calculation of the total stresses. That is the sigma set. So here you will find that yes, we have the stresses varying from a zero value at the top to a value of maximum value of minus 38.7 kN per meter square is the total stress. And if you hand calculate it, you will find that it's coming around say 435. It matches very well. So now let us go and see the effective stresses. So Cartesian effective stresses. Obviously, from this total stress of 438.7, we need to subtract the pore water pressure. So we can have a sigma dash set. So you find that you are having a lesser value, that is minus 268.7. This also matches almost well with the hand computed values. So this is all about the initial phase, which takes care of only the vertical stresses and horizontal stresses. Please remember that in the initial phase, we don't have any kind of a shear stresses developed, especially in the case of K0 procedure. Accordingly, if you go and go to the deformations and press for the phase displacements, you will have to find a phase displacements of zero. That means in the initial phase, you need to ensure, you need to check that no displacements are being calculated. So here we find that there is no displacement. So this means that the calculations performed in the initial phase is in line with our expectations. Now we are ready to proceed to the intermediate, that's the phase 1 is not relevant to us. And let us go straight to the phase 2, which represents the column applied loads. That's under dilute plus live load plus wind load case. So in this case, first of all, I would like to see the deformations. So let me go to the deformations tab. So I will see the phase displacements. That means UZ. So we find that this is the deformation, the variation of the deformation. However, from this 3D model, we are unable to see it across the depth. We'll take a cross section later. So here you will find that the maximum displacement or the maximum settlement is of the order of 124.7 mm. Okay, so this value need to be now compared with what is allowed from the bearing, what is being used for the bearing capacity calculation, etc., or what is the maximum settlement that is tolerated by the structure. You have to take all these things while before accepting this value of 125 mm. Now I want to take two cross sections here, one vertical and one horizontal, to see how the settlement varies across the depth. So this can be easily done. So if you see that here we have a tab known as a vertical cross section. So you just press this vertical cross section. Now here, rather I want to see across the width because the width is very critical for me. So I would like to inspect what will be the variation of the displacement across a vertical cross section that is taken along the shorter dimension. So obviously along this dimension, my x should be 0. So I'm taking a cross section just across the mid dimension of this raft. So this my x, I would like to take this set as 0, and here also my x will be 0, and the y I want to vary, for example, from say minus 50 minus 50, because this is not required. Say minus 32 plus 30 should be good enough for me. 30 should be good enough for me. Okay, so this is okay. So now you'll find that yes, let me just use the camera. Now here you will find that yes, this is the variation of the stresses. So let me just go to the view button, the mesh, because we can see the tools. So I can activate or deactivate this particular structure. In the geometry, if you see, there's a show structure on cross section, show all structures. So you can see that yes, now the cross section is very clearly visible to me. So you'll find that yes, this is how the displacement varies, or it is something like the maximum displacement at around z equal to minus 4 meter. And here please note that we have this almost the same displacements, because when the footing settles down, what exactly to do, it takes some of the soil along the side shores along with it, because we assume in this calculation that the side loads are also active in mobilizing the resistance. So that's why you find that all these contours extend up to the top surface rather than from the bottom surface of the raft. So here we find that the maximum displacement is of the order of 124.2. So now suppose you want to, for example, in the geometry, if you want to see the structure also, you can see the structure. You can just structure means here we have the structure as only the raft. Okay, the raft, that means it consists of the floor as well as the walls. So this is how it looks like. Okay, fine. So now it is also possible for you to move this cross section across the length of this raft. So what you need to do is that you have to press Control and then do the plus. Okay, so you'll find that yes, it is moving across the various dimensions, and you can also read here how the maximum displacement is getting changed. So if you see here plus, you find that yes, it is moving. It's moving beyond the raft now. So beyond the raft, you find that suddenly there's a decrease in the settlements or the displacements that is observed. So you can move it to, if you want to move it again forward, you can use a minus sign. You can see that this is how, for example, you can just rotate it a little bit up also. Okay, so just press it and you can see that control minus, if you see it is moving across this, and once it comes, you will find that the displacement contours it drastically reduces. So within the raft, we find that we have the settlements of the order of a maximum. So you can see that is coming, this maximum settlement comes almost at the mid depth, is 124.5 mm. Okay, fine. So we can also inspect the so-called vertical stresses here. So okay, fine. So let me just go back. So in the when you want to inspect what will be the additional stresses in the soil due to this dead load plus live load plus wind load, there is one problem which I want to highlight here. For example, if you go to the stresses, unfortunately, if you go to the deformations, we have got two things. One is the total displacement and the phase displacements. But when you go to the stresses, unfortunately, we do not have anything like a phase stresses, which means that it is almost impossible for us to calculate what exactly is the new stresses or the incremental stresses generated due to dead load plus live load plus wind load. Or maybe that we have to calculate the total stress, subtract it from that, subtract the initial stresses, which has to be done by manually. This is one disadvantage that I am observing in PLAXIS here. So anyway, so let us see the variation of the stresses. So I would like to inspect the first of all the total stresses sigma zz. So just like we did in the earlier case, we can also see the vertical. We can also see what will be the variation of the stresses across the depth. So please remember that this is actually the total stress. Though the phase selected is a dead load, live load plus wind load, this also include the stresses due to the initial conditions as well, or the stresses due to the self weight, right? We don't have anything like an incremental stress or the phase stresses here. So we can also proceed for example, we can take here the vertical stresses here as well, vertical cross section. So you can take a vertical cross section. For example, you can write it here. It is as x0, x0, and I want to keep my y as, for example, say minus 30, x0 here, and here I want to keep it as a plus 30. And this is being done just to see what will be the distribution of the stresses across the vertical cross section. So here you will find that. So let me just rotate it a little bit. Okay, fine. That's good enough for me. And let me also remove my from the geometry my structures. Okay, so here you'll find that right at this level. So if you include in the geometry my structure also, that means at this level. So the color, you can see that the color is almost this something like this. So this is almost a 125 kilonewton per meter square. So this is the maximum stress. And don't be carried away by this 462. 462 is the stress that is coming here, which is essentially due to the self weight. But the incremental stresses that is coming, or total stresses that is coming under the phase of this under this particular stress phase is almost like I say 120 kilometer per meter square. So that's okay for us, and we can carry out, we can cross check this with the other allowable value of the allowable value of the bearing capacity from the shear consideration. So right now we find that the under the raft we observe a maximum stress of the order of say 125 or around 120 kN per meter square. So having done that, it's also possible for us to inspect to inspect the results of the plate elements as well. So for example, we will be able to see what will be the bending moments as well as the shear forces in the plates. So let me just go to the geometry. First of all, let me just deactivate this solid volume. Okay, and so that I will get my plates. So if you just double click my plate, okay, so this means that okay, we are having so let us see the forces. So for example, if you're seeing the M11, you'll find that okay, let me just do this. Okay, so you'll find that this is how the M11 the bending moment varies across the length of the raft, and here you'll find that the maximum bending moment is of the order of say 1500 kilonewton meter per meter width of the raft. Okay, so also we'll find that the the raft bending moments are different. That means around the as expected around the columns we find the maximum locations of the occurrence of maximum bending moments. And you can also see in the forces, for example, you can see the M22, that is the bending moment in the other direction, wherein we find that here we have got 17,000 kilonewton meter. So that is again occurring at the locations of the columns. And we are also, it is also possible for us to see the variation of the shear stresses. So you can see that this is how the shear stresses varies, and it provides you the shear stresses in kilometer per meter. And this could be easily used for the design of the raft. So that's all regarding this tutorial. So it's also important that we perform some manual calculations of the actual pressures and the settlements based on our fundamental knowledge in geotechnical as well as the structural engineering before accepting the results provided by the PLAXIS. So that's all. So thanks a lot. Bye.